Today, as you know, is the 104th anniversary of general theory of relativity. Einstein gave his final form of general theory of relativity on 25th November 1915, and today is its anniversary. Because he was familiar with what happened in electromagnetism, and since his theory is a relativistic theory of gravity, he immediately realized in the next year that there must be gravitational waves predicted by his theory. So he predicted in 1916 as an important consequence of general relativity using a simple version of his theory which we call linearized gravity. And in 1918, he gave what we call today as the quadrupole formula, which is analogous to the dipole formula which we have in electromagnetism, which basically says that the gravitational wave perturbation falls off as 1 by r. It is given by these fundamental constants, and it is given by the second time derivative of the quadrupole moment. Remember, the dipole formula has the first time derivative of the dipole moment. So if you take this simple formula and apply it to a system which moves with velocity v and has a mass m, then this simple formula reduces to this following combination, where m is the mass, v is the velocity, and r is the distance from the source. And then if you apply it to a simple numerical problem where you have two trucks separated by a couple of meters rotating at about a kilohertz, then the value of h comes out to be 10 raised to minus 39. And remember, Einstein worked in the patent office, and therefore he realized that this must have practically vanishing value in all conceivable situations. Such ripples would be vanishingly small and nearly impossible to detect. And of course he was right, because it took 100 years to make the first detection of gravitational waves. What happened over the next 50 years? Over the next 50 years, there was essentially a babble around this whole idea of gravitational waves. For example, immediately in 1922, Eddington pointed out that though Einstein derived his formula, it does not apply for self-gravitating systems. And also that if you analyze the equations, it looked like gravity waves could propagate at any speed you can imagine. 1936, Einstein added to the confusion when he wrote to one of his friends, together with a young collaborator, I arrived at the interesting result that gravitational waves do not exist. But by the time the paper was finally published, since that he was making some erroneous interpretation of the analysis, and by the time the paper was published, he retracted this particular claim. The basic question was, do gravitational waves actually transfer energy like electromagnetic waves, or they are an illusion because we are choosing coordinates which are wavy? This is really the physical question which you have to answer. And people like Feynman, for example, in 1957, was very frustrated by all the mathematical discussions which were happening in relativity. And he said, supposed to have said, drive on, make up your mind, don't be so rigorous or you will not succeed. He then goes to another relativity meeting in 1961 and finds that the physicists, relativists are still discussing about gravitational waves. And then he writes to his wife and says, a day to discuss do gravitational wave carry energy, it's not good for my blood pressure. So you can see here that for almost 50 years, the actual status of gravitational waves was not very clear, and it took almost 40 to 50 years to set up a conceptual framework so that you could say without ambiguity that gravitational waves exist in general relativity and what are the properties of gravitational waves. It almost took 50 years. And if you ask what are the technical complications, it was really related to the fact that people were confused about whether singularities are coordinate singularities or whether they are physical singularities. What kind of boundary conditions you have to use to discuss radiation? If you use an approximation scheme, how do you impose boundary conditions in that approximation scheme? All these technical complications made the analysis very, very difficult, and it was sort of realized that if you have self-gravitating bodies, you have a technical complication because the potential is of the same order as velocity by the virial theorem. So if you want to calculate higher order corrections, that is v square by c square corrections, you have to deal with the nonlinearities of Einstein's equations. You cannot deal with the linear version of Einstein's equations. And as you know, dealing with nonlinearities is not a simple exercise. So therefore, there were many different approaches, one due to Einstein, Infeld and Hoffman, another by Landau, Lifshitz, and another by Fock. And these are the prototypes by which we do the analysis even today. In 1960s, there was an important result when Chandrasekhar attacked this problem by following work which was done earlier by Trautmann. the question he wanted to answer was, how does the emission of gravitational wave affect an emitting system when it is self-gravitating? And then by analysis of the equations, he could show that the energy and angular momentum which are radiated as gravitational waves, they are correctly balanced by the loss of mechanical energy and angular momentum from the system. And this gave astrophysicists confidence that GR was physically reasonable and well behaved. So you can see here that 50 years after Einstein predicted this, you come to a situation where you believe in the physicality of the gravitational waves. A very important historical event was the Chapel Hill meeting in 1957, where Pirani, who was a postdoc with Bondi, essentially made the point that if you look at the tidal effect of gravitational waves, they are unambiguously given by the theory. And therefore, if you look at the geodesic deviation equation, then there is no doubt about whether gravitational waves are passing through a region of space or not. And immediately in that meeting, when there were discussions with Bondi, the physicality of gravitational waves was sort of resolved. They basically argued that if you had a kind of rod on which you put some washers which could be sort of moved, if gravitational waves fell on it, they would be tidally moving, and that friction will heat. So you are converting gravitational waves into heat, so that really means that gravitational wave is a physical quantity. And immediately, once the physicality was understood, we can say that the quest of gravitational wave detection was born, because in this meeting, Joe Weber and John Wheeler were there. So after going back from this meeting, Joe Weber built his first detector of gravitational waves, which was a bar. And in a sense, even though there was a lot of confusion before, the first experimental search for gravitational waves really began. In parallel, the discussion of gravitational waves in the full general theory of relativity was sort of finalized by Bondi and his collaborators. So we moved from the babble around gravitational waves to actual search for gravitational waves. And as I said, the first search for gravitational waves happened by Joe Weber, who built a bar detector in 1960. But then, in 1969, he made the claim that gravitational waves have been detected by his detector. But when other people tried to reproduce his experiment, they found that experiment his results could not be reproduced. So in a sense, we consider him as a kind of tragic pioneer, and it almost took 50 years before the instrument which could make the detection for gravitational waves was built. And in the meanwhile, the following changes had to happen. Instead of bar detectors, we had to use laser interferometers, which are more sensitive instruments. Bar detectors are sensitive in a small region of frequency, so we call them narrowband detectors, whereas the laser interferometers are broadband detectors. And the sources which we were looking for were supernova, and as I will argue now in the next few slides, the sources which are our favorite prototypes are coalescing compact binaries made up of neutron stars and black holes. So in the 50 years since he built his first detectors, many of these changes were possible, and this is what really allowed for the detection of gravitational waves. Before moving ahead, let us ask the following question. If you analyze the equations of general relativity as you analyze electromagnetic equations, you can talk about the properties of gravitational waves. And the properties are the following. They travel at the speed of light, they are transverse, and they have two states of polarization. So you can see here that it is exactly like what happens in electromagnetism. Just as electromagnetic waves carry away energy, angular momentum, and linear momentum, gravitational waves also carry away all these quantities. Just as accelerated charges create electromagnetic waves, accelerated masses create gravitational waves, and there are differences. Those were similarities. The similarities are because of the fact that the gravitational interaction is about 10 raised to 39 times weaker compared to electromagnetism. So gravitational waves will propagate unperturbed through space as they interact weakly with matter. This allows you to do the following. You can observe gravitational waves even if they are emitted inside a supernova, even if they are coming from the first events of the Big Bang, because you can see photons from, let's say, 100,000 years after the Big Bang, neutrinos around 1 second after the Big Bang. But you can see gravitational waves from 10 raised to minus 43 seconds after the Big Bang if gravitational waves are emitted there. So you can see here that what gravitational waves tell you is an undisturbed picture of the universe. Unlike electromagnetism, gravitational interaction is non-linear because of the fact that the wave energy itself will have a gravitational field. So, technical calculations in gravitational waves becomes much more complicated, but the important point is that these properties of gravitational waves which I am talking about come from general theory of relativity. If your theory of gravity is different, the properties of gravitational waves will be different, and therefore eventually by using gravitational waves you will be able to test Einstein's general theory of relativity. As I told you, many things happened in between, and one of them was the discovery of pulsars. In 1933, Bade and Zwicky said that at the end of stellar evolution, neutron stars should be sort of formed as end states of supernova explosions. But nobody knew how to look for neutron stars. Now, what are neutron stars? Neutron stars are stars as massive as the sun, but of radius 10 to 15 kilometers. So, if you put these two numbers together, you will see that they are at nuclear densities. So, neutron stars are like giant nuclei. But how do you look for them? Now, in 1967, while looking for radio sources by scintillation, Jocelyn Bell, who was a graduate student like you, and Tony Hewish, who was her advisor, were trying to study something else when they found a source which was very, very, rotating with very, very precise period. So, when they tried to interpret this particular source, they essentially realized that these are nothing, they cannot be anything else but rotating neutron stars, and that is what we call as pulsars. Now, the important point is, for the discovery of pulsars, the Nobel Prize was given to Hewish and Ryle. It was not given to Jocelyn Bell because she was a graduate student, but we are all very happy that in 2018 she was given the breakthrough prize for discovering pulsars. I also would like to emphasize that these are areas where a graduate student can make breakthrough discoveries, as you will see in the next slide. Once pulsars were discovered, radio astronomers started looking for more and more kinds of pulsars, and in 1974, another graduate student, Hulse, who was working with Taylor, was trying to look for more pulsars, and at that particular point they came up with a pulsar which was slightly more unusual. This pulsar was unusual because by using pulsar timing, you could reconstruct the orbit in which this object was sort of moving, and this is by using radio observations. And then you suddenly realize that you have in the heavens a kind of dumbbell, and if you believe general theory of relativity, this system should emit gravitational waves, and instead of moving on a fixed orbit, it should spiral inwards, and you should see a signature of that in spiral in the gravitation, in the measurements which you are making. And this exactly is what Weisberg and Taylor basically did. They looked for this system for about 4 to 8 years, and at the end of 8 years, they could say that what the observations were really matching with what Einstein's theory predicted and not with what Newton would have said. So, in 1993, for this system, and as you can see here, this system has been observed for almost 30 to 40 years, and all the points which are dots here are observations, and the thick line is the prediction coming from Einstein's general theory of relativity. So, you have radio observations, which is an indirect observation, which tells you that binary systems lose energy by gravitational wave emission. For the discovery of this particular object, these two gentlemen, Hulse and Taylor, were given the Nobel Prize in 1993 because by using them you could study general theory of relativity even more accurately. Are there other pulsars which have been discovered? Yes, later on many other binary pulsars have been discovered, and every time you try to make this kind of plot, you match with what Einstein predicted. Now you are in a situation, remember, for 50 years people didn't believe in the gravitational waves. When the match became so exact, people started asking the question, why is this formula working at all? Because this formula was derived by using linearized gravity. Now we are talking about two neutron stars which are strongly gravitating and going around each other. So why is it that a formula discovered in an approximation matches so well in a situation where the system is very, very relativistic and very, very strongly gravitating? So there was a controversy when this system was discovered, and in the theoretical work of people like Damour, Walker and many others, one could understand that there was a fundamental reason why the linearized gravity results should match even when the system is strongly gravitating. It is basically because of what is called as the effacing principle which happens, which in some sense effaces the external information on all the neutron stars. Whether it's a neutron star or an ordinary star, it does not really matter. What really matters is the mass of that particular object, and the quadrupole formula applies even for strongly gravitating bodies. So now you are in a situation where you can put together two very different things. We have a quadrupole formula for Einstein, and we have a binary neutron star system which is sort of inspiraling inwards. So you can ask the question, what will happen to this particular system when you wait for a long time? Let's say you wait for about 300 million years. So remember, these two objects are very far. Because it's inspiraling, it's coming closer and closer. And finally, after 300 million years, they will sort of hit each other. Why is it possible? Remember, if it is an ordinary star has a radius of about 10,000 kilometers. So it will not be able to come very, very close. But a neutron star is almost like a point. It's only about 10 kilometers. So it can come very, very close. And therefore, the frequency at which you can see this particular neutron star binary has a very special role in what you will see next. So immediately by putting these things together, we can say that in the universe there exist inspiraling neutron stars which will emit gravitational waves for hundreds of million years before they coalesce spectacularly. And when they coalesce, at what frequency do they coalesce? So one can show that the late inspiral of these binary neutron stars happens exactly in the bandwidth where you can build the sensitive detectors. You can build sensitive laser interferometric detectors in the frequency range of about 10 hertz to about a kilohertz. And when it's about to coalesce, the frequency of these systems is roughly of that same order of magnitude. So you can see here that many things had to come together. First, you have to have such a system, you have to have a detector, and you have to have a detector which is sensitive exactly in those frequency ranges. And as I have been sort of saying, there are other binary pulsar-like systems which have been seen. If this coalesces in about 300 million years, other binary pulsars will coalesce in about 80 million years, and one of them in even about 46 million years. Now keep in mind that though it looks like a very large amount of time, millions of years, the age of the universe is in billions of years. So compared to the age of the universe, this is very, very small. So in the universe, even though this binary pulsar is not coalescing, maybe there are other binary pulsars which are currently coalescing. And that is exactly the kind of sources we are looking for. So you have to ask the question, what kind of tidal force fields are created in general theory of relativity? And then when you do the analysis of Einstein's equations, you will see that the tidal forces act along a plus direction or along a 45-degree turned direction, which I call the cross direction. So the force acts like this. So if this force acts on a ring of particles, the ring of particles will be squeezed and elongated with this time-dependent profile which is sort of shown here. So if you want to detect gravitational waves, you should be able to measure the small squeeze which is happening here. I am exaggerated in this diagram, of course, the squeeze. So the important point is that find out how much squeeze is happening. If you can measure that squeeze, you can measure the presence of a gravitational wave. So to quantify it, you define the notion of what we call as a gravitational wave strain. If you have two bodies which are separated by a distance L, and because of the action of gravitational waves, if they are squeezed and elongated by an amount delta L, just take the ratio of delta L by L. This is a dimensionless quantity, so we call it the dimensionless strain. So if your H is fixed, if you want to have a large delta L, you should obviously have a large L. So that is the reason we really want to build as big an instrument as sort of possible. You cannot do this measurement by building an interferometer in the laboratory. You need to build large-scale interferometers, and that is exactly what we do. So what we do is, now we ask the question, I know there is a binary neutron star system, I know its mass, I know, let me sort of put it in the nearest cluster of galaxies, which is the Virgo cluster of galaxies. And then you ask, what is the strain it will create in a detector if I have it on the Earth? Then you find that the strain it causes is not 10 raised to minus 39. You remember, I gave you a number which Einstein talked about, that if you have a laboratory source the strain it causes is 10 raised to minus 39. If you have an astrophysical source in the nearest cluster of galaxies, then the strain it causes is 10 raised to minus 21. So if you can build an interferometer which is a kilometer long, then the displacement you are needing to measure is 10 raised to minus 18th of a meter, which is smaller than the nuclear dimension. So in something which is a kilometer long, you want to measure something smaller than a nuclear dimension. And that exactly is the reason why you basically have to wait for so long, because if you compare with what you measure when you do the Michelson-Morley experiment, you find that what you are measuring is about 10 raised to minus 9th of a meter. So in 1905, when we were talking about the Michelson-Morley experiment, this was the displacement you could measure, but what we need to measure to detect gravitational waves is 10 raised to minus 18, almost 10 orders of magnitude. So if you assume that technology improves by a factor of 10, it would take about 100 years, and that's exactly what happened. So the important point you have to sort of keep in mind is that the laser interferometers we have sort of built is the way in which we want to detect gravitational waves, and the person who basically began thinking about it to use laser interferometry was Ray Weiss. In a paper which he wrote in an obscure journal of MIT, he basically tried to use the idea of a laser interferometer to measure small displacements. Now the important point you have to keep in mind is you may have a very sensitive instrument, but that instrument, if it is subject to many other sources of noise, you would not be able to make this very small measurement. So what you really have to make sure is list all possible sources of noise which will cause displacements much more than this particular gravitational wave signal. So he did this first detailed noise sensitivity analysis, and he realized that the interferometer is subject to shot noise, radiation pressure noise, thermal noise, seismic noise, gravity gradient noise, etc. And he made an estimate by using standard physics of what will be the value of displacement which these different noises will cause. And then from this there was a small proposal developed which is called the Blue Book, and finally in 1989 the whole thing got converted into a proposal to the NSF for creating the LIGO detector. Now, how do you gain that extra 10 factors in going from the Michelson-Morley experiment to this? A simple Michelson-Morley experiment, if you build, even if it's a kilometer long, it is not sensitive enough. So what you try to do is use all the tricks which you know, and one of them is to use the fact that if you can increase the optical path length by using Fabry-Perot cavities, then essentially you are increasing the length of the interferometer. So you create a Fabry-Perot cavity in which you bounce light 100 times. So even if you have a 1 kilometer long interferometer, it's like having a 100 kilometer long interferometer, because you're storing the light for that particular amount of time. Then there are techniques to improve the sensitivity at high frequencies which are called power recycling. So you do power recycling about 50 times. Then there are techniques which are called signal recycling. And of course, you build specialized photo detectors, and putting all these things together, you can measure not just the displacement between two fringes, but you can split the fringe and measure 10 raised to minus 11th of a fringe. So this is what really allowed you to go beyond the standard interferometer. So we can say that the interferometer acts like a transducer. It's converting the gravitational wave to a photocurrent which is proportional to the strain amplitude. So you are measuring this small photocurrent by all these techniques which you have put together. Now when you ask the question, if I have an interferometer, does it have the same sensitivity at all frequencies? Then it turns out that because the noises are different at different frequencies, the sensitivity of the interferometer is different at different sensitivities. So what is shown here is the different frequencies and the sensitivity, the displacement it can measure at those different frequencies. So for example, if you ask at high frequencies, that means frequencies in this particular range, how do you get this sensitivity? You have to use high power lasers. The power recycling helps quite a lot. If you want to achieve this sensitivity, you really have to control the thermal noise. So you really have to build mirrors which have lower thermal noise. And then the most challenging thing is that what happens when you go to lower frequencies. Now it looks like I'm standing on a very stable earth, but this earth underneath my feet is moving quite a lot. It moves almost 1 nanometer. And I'm trying to measure 1,000th of a Fermi. So obviously my interferometer is being pushed around a lot. So the only way you can manage this is by having better vibration isolation. You build, in the car you have the shock absorbers. So you do exactly something like that. You put, you try to isolate the interferometer by using passive oscillators and active isolation, and you can reduce the displacement by factors of 10 raised to 10. And putting all these things together, essentially, you really push instrument science to the frontiers, and what you really need to achieve are limits which are at the limits of what you can do by physics today. So you can see here that it is the requirement to do all this, and it's not only about general theory of relativity. It involves lasers, coatings, materials, vibration isolation mechanism. So everything has to come into place, and all this technology is available only today. It was not available 100 years before. Even after putting all these two things together, the LIGO guys realized that they were fighting for something which was much more complicated. So they felt that they should be more careful. They should try to make sure that when they say they have seen an astrophysical signal, they can be very sure about it. So what they decided was that they would believe that they are seeing something astrophysical only if they saw it in two detectors put as far away in the US as possible. So they built one interferometer in Hanford, one at Livingston, identical 4-kilometer long interferometers, and for the rest of my story, sometimes it will be very important, they were even more careful. At the Hanford site, in the same beam tube, they put two detectors. So they had two sites and three detectors, and at each site you try to look at all possible other sources of noise, so that after removing all of them, if something still remains, only then you will claim that you have seen an astrophysical signal. So you should see a signal in this LIGO and this LIGO, and since they are at different places, even if light travels at the speed of, if gravitational waves travel at the speed of light, they could come at slightly different times. So the light travel time is about 10 milliseconds between these two sites. So you should see a signal within the 10 milliseconds, then you will see that it's an astrophysical signal. The Europeans built their own smaller detector, which is 3 kilometers, which is called the Virgo detector, and today these are the three big detectors which look for gravitational waves. So it was an important point to emphasize that this instrument is the most sensitive instrument on the earth, because it can measure this very small displacement, and it was really put together by a set of very talented instrument builders who really worked on it almost all their lives. If you look at the people who work on this particular project, they started as PhD students, and when they began they had hair on their head, but now most of them are bald.